Hello everyone, this is Mandeep Singh Shekhawat and I am back with another discussion video in which we will be talking about DoorDash search engine. So search engine, as you can see from the term, is a system which is responsible basically to help you with the searches which are carried on top of your platform. So in case of DoorDash, if you don't know, it's a food platform similar to Zomato or Swiggy in India. So what you do is you go to the app, okay, you go to the platform, you perform some sorts of search. Let's say you want biryani, okay. This search goes to your search system, you get some results and those results are reflected in the application. So this is what a basic responsibility of a search. There is some data ingested on which you provide some sort of keywords, and then on top of that you perform the search. So this is the basic architecture of the search system, and we will be discussing the architecture very specific to DoorDash, how it was designed at DoorDash. Okay, so and this is based on this particular blog which is published by DoorDash on their engineering blogs website. Cool. So before we get started, if you haven't subscribed to the channel MsDeep Singh on which you are watching the video right now, consider subscribing. You will get to learn a lot of these concepts and get to have all these architectural discussions which I keep on having regularly. I try to publish these videos, and there is also a book, System Design on AWS, which I have written along with Jayant, which is a great book and will help you to learn how to design systems, which is divided into three parts: part 1, part 2, and part 3. Part 1 basically talks about all the system design concepts, okay, like let's say load balancing. This is one of the concept. How then there are a lot of things like containerization, how you deploy all those things. So a lot of concepts, whatever you can think of on the system design level, what are the base concepts you should know of when you are actually designing the systems. Part 2 actually talks about AWS services. So there are different domains in which there are multiple services AWS provides. Let's say in compute you have Elasticsearch, in compute you have EC2, then Lambda, then ECS. Okay, in similarly for databases you have multiple services: DynamoDB, Elasticsearch for search. Okay, in case of AWS it's open search. So then RDS, Aurora, all those things. So there are multiple services. You will learn about those services, what are the key differences between them, in which scenarios you should use particular service. And then part 3 has multiple exams, not exams, multiple examples of how you actually design the system. Okay, and one of the chapter is designing web crawler and search system. Okay, so in that chapter we talk about specifically how will you design a system like Google and how you can actually deploy it on AWS. So if you see a lot of discussions on internet right now, there are very few things or few discussions where you will find how you will actually deploy the systems, or how, if you want to leverage the multiple AWS services, or if there is a possibility of using a custom based solution which you should build. So part 3 is all about that. So it's a combination of your base concepts and then AWS services, and then how you actually implement them, how you actually use those concepts and AWS services to build the systems. So go check out that. It's a O'Reilly book. You can check out on the platform, and it will be available soon in the hard copies format in month or so. So you can go buy that as well. It will be available on Amazon and multiple platforms. It's already available for pre-booking right now. Coming back to our discussion, which is designing search system. Okay, I hope you are convinced that this is great book and you are watching the video on this great channel, which you should subscribe to MsDeep Singh. Cool. Now, coming back to our discussion, what we are discussing today, we are discussing about DoorDash search architecture. So, depending based on the engineering blog which is written by DoorDash, they were using Elasticsearch. Okay, they were using Elasticsearch, and it's a pretty common solution when you talk, when you can think of use cases like search. Okay, it is heavily used by multiple companies. If you see, Netflix uses Elasticsearch. A lot of companies use Elasticsearch for their search use cases, and it works well. But in case of DoorDash, they faced some sort of challenges with Elasticsearch. Okay, if you haven't heard of Elasticsearch yet, okay, it's your kind of, what you say, in managing inverted indexes basically in some fashion so that you can perform those searches easily. So Elasticsearch is your management of inverted indexes, which is built on top of Apache Lucene library. Okay, Apache Lucene is, this is the term which you will hear a lot if you talk about the search systems, developing search system. Okay, so there were few challenges which they were facing, the DoorDash team which were facing. Before going to the issues, right, let's talk about a little bit about Elasticsearch, like what Elasticsearch is. So as I mentioned, it's what you can, in a very simplistic term, you can say it's a management of inverted indexes. So there are few terms in Elasticsearch, and we will try to compare it with the RDS table. RDS as in your relational DB. Okay, let's talk about Postgres. So we'll try to compare it Postgres table and databases. Okay, so what is ES? ES is your management of inverted indexes. Okay, combination of inverted indexes where you perform the search. There are few terms which are specific to ES, which is, first one is index. Index is much similar to your RDS table where you push the data. Okay, where you push the data. So you can define the schemas at index level. So let's say you have created some weekly index where you push the data, and once your new week arrives, you create a new index. Okay, so it's much similar to your RDS table. Now this index is further divided into shards. So you have index, and then further it is divided into shards. Okay, shards are further divided into segments, and segments is combination of documents. So this is, you can say, hierarchy of how or what data structures, or like what, in which format the data is stored in the Elasticsearch basically. So your index is similar to RDS table, then this is further subdivided, you can say sub indexes, which are shards. So shards are indexes which are further divided into sub indexes, and they are called shards. Okay, search is performed on these shards. Now this shard is combination of segments. Okay, so this segment is a data structure, immutable data structure. When I say immutable basically means it is not updated. Okay, it's not updated. You write it, you then delete it. Okay, you don't update that particular entry. Okay, so this segments are then stored on the shards, and a segment is basically your inverted index. Okay, so you have multiple inverted indexes, they are kept on a shard. Shards are stored in the index, and they are also these shards are replicated. Okay, so let's say this is my Elasticsearch cluster. Okay, so let's say this is my master node, and then you have your data node D1, D2, and then D3. Okay, so your data will be replicated. So you have S1. Okay, you have S1 dash, which is replicated, let's say depending on the replication factor, the data is replicated on two shards. Similarly, you have S2 here. Okay, then it is replicated on these two. Okay, similarly, you do that replication to ensure that the read queries can be faster, like also from the redundancy standpoint, that your data is replicated in multiple places. So if one of the data node goes down, your queries, or like your system, is not losing that data, or you have that log maintained how your data is kept. And your document is final structure in which the data is kept. Okay, the schema in which your data is storing. So let's say talk about RDS. I keep on saying RDS, it's relational database service for AWS. But if we talk about Postgres table, right, so it has multiple rows. Let's say you have ID. Okay, you have some text. Okay, so for ID1 your text is Mandeep, for ID2 your text is Singh. Okay, so similarly you have these documents created. You see these, this is one row, this is another row. So these are your documents which are kept in the Elasticsearch. Okay, so I hope you got the basic gist of how the data is kept in the Elasticsearch. Great. Now coming back to what were the issues with the architecture, due to which DoorDash has to consider a new solution, a custom built solution for their use case. Okay, so let's talk about the issues. So issue was document replication mechanism. Okay, one of the issue was the replication mechanism was at a document level, something of like, and they basically wanted segment level replication. Okay, uh okay, just to update what I said earlier, I said that shards are replicated. So when I say shards, I basically meant the data is replicated for all the entries which are kept. Great. So this is first issue, that there was a document replication mechanism. And when I say issue, it's not issue as per like Elasticsearch. Okay, it's issue as per DoorDash architecture, that they were not getting the results as per their expectations. Okay, their search was not actually working as per their expectation. So this is a particular problem with this DoorDash architecture. Okay, so just think of these issues just in the context of DoorDash architecture, or how their systems are implemented and how they are leveraging Elasticsearch to implement their search functionality. Lack of support for complex document relationships. So they DoorDash basically wanted a support, something, let's say you do joins in relational tables. Okay, you do ordering of some sort. Okay, this document should be ordered based on some ascending order or so. So you want to perform multiple complex relationships, much similar to your RDS or Postgres, which was missing in Elasticsearch by default. Internal capabilities for query understanding and ranking. So they didn't wanted to use their like whatever is provided by Elasticsearch. They wanted something of a custom. Okay, which understands their query, okay, their custom query, and then also performs the ranking depending on their own algorithm. Great. So these were the issues, not great, these were the issues which were faced by the DoorDash system. Now, what was the solution? Solution was, you are still using Apache Lucene. Okay, Elasticsearch is built on top of Apache Lucene, so you are still using Apache Lucene, and on top of it, you are writing your custom logic. Okay, leveraging, because the basic logic is same, that you are creating inverted indexes, and then you are dumping the data to those inverted indexes. We are just trying to improve on the upper level, or like higher level architecture, how you are managing. Also, you are doing segment level replication. This is first thing. There is separate component for indexer and searcher. So if I talk about the Elasticsearch architecture, okay, I mentioned that you dump the data into documents. Like document is the final entity, or a entry in which data is dumped. Okay, so how the data is pushed? So let's say this is your master node. Okay, so this pushes the data to your, this is your document, and this is stored in your segment and then in your shard. Okay, so this document is stored, and then you are performing the search on this document itself. Okay, these are the search queries. So what DoorDash wanted is, this document is created. Okay, when I say separate indexer and searcher, so the indexer work is to store this, index this document. Okay, index this document, and then searcher component is not performing directly search on this. Okay, this document is pushed somewhere else, and then it is stored somewhere else. Okay, we will go to the architecture and then we will understand more in detail. So basically, you are trying to independently scale them, or independently maintain your index component and search component. If we talk about the search architecture, you are ingesting the data, so that is indexer, and then you are using that data to solve your read queries, so that is your search component. We will try to understand with help of diagram below that how they are independently maintained by DoorDash system. Okay, third point, indexes store multiple type of documents with relations between them. So uh, again, this is much specific to DoorDash architecture, because they wanted certain functionalities which I've mentioned right here: internal capabilities for query understanding and ranking, plus lack of support for complex document relationships. So they wanted these features. Okay, they are not by default provided by Elasticsearch, so they build their custom solution, and then this solution is basically serving those requirements. Great. So this is the architecture. This is the architecture. Now if we talk about the architecture, how it works, basically, let's take an example from first. We will try to, okay, this is your data dump. So you have your something called indexer stores the data here. Okay, then you have searcher, which looks for the data. So this is the, you can say, a very high level view of how search system works. Now how it is working in case of DoorDash. Great. Let's first talk about the indexer. Okay, so you have client. When I say client, you can assume in case of DoorDash, let's say client is a restaurant onboarding system. Okay, restaurant onboarding system, or I mean, you can say food on basically our onboarding system which is onboarding or which is pushing more data to the system. So there can be multiple clients. What clients do, client will push the document. When I say documents, it's basically your data. Okay, the data. So this is some schema which is provided by the document, like the internal architecture which is built on top of, you just call this search stack, in which the data is pushed. Okay, so the document store, and then the data is finally stored by the document indexer, and then they are pushed or like uploaded to the S3. You can say that multi-part upload is used, but they are pushed to S3. So this is the overall work of your indexer. Great. So, and once the data is saved, what this searcher do, searcher will download these indexes. Okay, searcher will download these indexes to serve the queries. Now how queries are served, again you have multiple clients. These are internal clients at teams. Okay, one could be your front end application. Okay, so they come up with a raw query. Okay, they are provided some sort of APIs, how they can query to our database. You have a broker system in between. Now broker's responsibility is that API is abstracted out for clients. Okay, but this broker converts that query into a more relevant form which can be understood by the search system. Great. So this broker will retrieve the results, and then we also have a query. This is basically your how the query should be executed, much similar to your query planning engines in your Postgres. Okay, so this is how your broker will understand that, yeah, this is the data which I have to retrieve, and then the finally processed query is sent to the searcher to retrieve the data, and then based on some ranking which is done, and then finally the results are returned to the clients. So this is the overall architecture of the search stack which is developed by the DoorDash. We will try to understand some more terms. Indexer, I already mentioned. What is indexer? Indexer is basically responsible for indexing the documents. Now there are two things in indexer as well. Okay, so first thing is we want to ensure that our system is independent, or like it's not impacted by the traffic of the clients. Okay, so let's say if there is a heavy traffic, there is a client which is trying to push a lot of data to the, so instead of like scaling this indexer component to support this traffic, what I do, I will create a bulk, or like you can say this, I have a pre-processing layer in which the data is kept. Okay, in which the data is kept. Now this is divided into two components. One is high priority queue, and other you can say low priority queue. Okay, this low priority queue, the data is pushed in bulk. Let's say for 1 hour, I collect the data for 1 hour and then I push it. If there is a data which is of high priority, then that is pushed at the same time, let's say within 1 minute or within 5 minutes. But I will figure out those use cases. Okay, so this, what it do, it helps in, that my system, my indexer system is not dependent or don't have to scale depending on the client traffic up and down. It can work on a, let's say TPS. I generally work on TPS 5, which is very low, which I can support easily. So it will continue working on that, and then I will bulk upload the documents. Great. So this is a great strategy which is followed by the indexer. And one of the thing which you particularly face challenges is, like if you horizontally scale your system, it will uh, update the number of shards, which leads to redistribution of shards among the data nodes, and then it is expensive operation. So basically you are hampering and you are doing extra work which you can totally avoid if you follow this approach of offline, basically offline uploading of the indexes, offline uploading of the documents to our indexes. Great. This is what we talk. Oh, it's every 6 hours. So I took an example of every 1 hour, but yeah, it's every 6 hours, and it's basically configurable. But yeah, this is what is done. You upload the index segments to S3. Okay, and these index segments are then finally downloaded by the searcher component. Searcher is a replicated service. When I say replicated service, there are multiple stacks of a searcher which are available so that they can serve to the user queries. It can't work on the offline mechanism. It have to scale depending on the client traffic. Okay, so it's a replicated service. There is a tenant level isolation. We will talk about it, so that noisy neighbor kind of solution problem is not arising there. So it consumes the segment from S3 and then it serve the search queries. Broker service we already talked about. We are providing a higher level abstraction to the clients so that they don't have to understand how Elasticsearch, basically they don't have to understand the Elasticsearch terms. Okay, so if this broker, let's say if there is something instead of elastics, right now I have created a custom solution. Okay, now in future if I create another solution, okay, so this broker will remain same and this architecture can be changed easily, so clients are not impacted by it. That's what the main benefit of creating a broker system on top of what we have already. Cool. This is basically how the system is designed right now. A few of the features of it. So how the namespace is, there are multiple kind of fields. One is index fields, how the data is indexed. Computed fields, whatever is computed dynamically at the query time. Query planning pipeline defines logic on how to process row into finally. Okay, so basically your broker system, okay, this query planning service. So what you are doing basically here is, you are passing something, okay, and it is trying to, it basically converts that into a useful query, which is processed query, which we here mentioned, but which is passed to the searcher to finally perform the search. And there are also support available for SQL like APIs, which we mentioned earlier. We wanted that support, which was not available with Elasticsearch by default. So keyword groups, all the SQL like operations, filter, joins, or etc., local join or block, whatever we have. Okay, so we have built those features. These details are not available in the block, how these features are implemented in the backend, but yeah, these features are available with the new architecture. Now tenant isolation is the important thing. What I mean by tenant is, so if you have never heard about a tenant, okay, tenant, let's quickly understand. Okay, tenant, what is tenant? So tenant is basically, you can say, a client level isolation. Okay, so this is your service. Now this service has to support, this service has to support multiple clients. Okay, multiple clients. Now all the clients can have different requirements. Okay, all the clients can have different requirements. How can those requirements be met easily? And the most important thing is, operations of one client, data of one client should not be impacted by the operations or data of another client, which we know as noisy neighbor problem. Okay, so what we mean by this is, if let's say there are two clients, this is client 1, this is C2. Okay, if let's say this C2 TPS is 1000, okay, so this system went down, so this is also impacting client 1. I don't want that, I want complete isolation. So that's what we mean by basically tenant. A tenant is onboarded to the system with some set of configurations. Let's say what is the TPS which is allowed for this tenant, okay, or what are the queries which are supported for this tenant. Okay, so all those things, basically I'm replicating my service at multiple places so that I can independently scale my system depending on the clients and they are not impacted by one another. If there is something going wrong in my search functionality for the application, it should not impact other functionalities in the search. Okay, so you have collection of server services dedicated to one particular index. A tenant are isolated this way, so workload of what, this is what we want basically. Tenant, at a tenant level you are dividing it to tenant. Just okay, let's take one more example. If you are still confused with the tenant, okay, you might have heard of DynamoDB. Okay, DynamoDB is a AWS service. Now you create your own tables. Okay, you create your own tables and then you store your data. Now at dynamodb level, you don't have to worry about how dynamodb is storing their data, but there is definitely some isolation is placed and data of all the customers are not kept all together. Okay, there is some logical and physical partitioning in place which divides this data. Okay, and for all the clients, if let's say I have defined some configurations of RCU and WCU for one client, okay, and I have defined another configurations of RCU and WCU for client 2. Okay, so they are independent tenants which are onboarded to the DynamoDB system, and then they are storing the data, retrieving the data. Similar what we are achieving here as well. So Great. Another thing is control plane was one of the component. Control plane responsibility is it's an orchestration component which is responsible for stack mutation. When I say stack mutation, means replication. Mutation is updating of stack, okay, or replicating of stack. Basically, you are updating that stack, and how you are updating that stack? You are creating a new deployment, and then once the new deployment is up, you are decommissioning the old deployment. Okay, so this is basically a deployment strategy which you are maintaining on the schema updates, and it is done every 6 hours. It is again configurable, which has to be. Uh, a search can only consume an index produced by the indexer of same. So when I say schema updates, they are maintained, they are uploaded, or like they are downloaded depending on a generation. Okay, so that if there is a schema update, to ensure that there is a backward and forward compatibility, just to ensure that. So if it's an generation, basically means versioning. Okay, so if let's say my indexer component is of version 1, so your searcher will also work on version 1. Okay, so the version mismatch is not happening, and then it is not, what do you say, uh, do not create any issues if there is any version schema mismatch. Okay, so if it is uploading some data, let's say it is try upload some data in a field, okay, and it is also trying to search for, but in the version 1 it is not present, and it's, let's say, it on version 2, and in version 2 the field name was changed to Mandeep. Mandeep is not a field name, but yeah. So this can create problems, and that's how your generation or versioning helps. So I hope this is the view of the architecture. Basically, okay, you are uploading the document, you have indexer, you are uploading the index to S3. Okay, this is your indexer, you uploaded, then there are multiple searcher components which are downloading the index, and then broker is serving, querying the searcher to retrieve the data, and then finally it is served to the client. So this is all about DoorDash search engine architecture. I hope you enjoyed the video. If you did, consider subscribing channel MsDeep Singh, and do check out System Design on AWS, which is, as I said, it's a great book. I'm pretty confident it's a great book which will help you understand system design as a whole, and how you will design or build systems on AWS, just not on AWS, on any cloud provider. So I will see you again with new such great discussions. Till then, stay safe. Tata. Bye bye.